Okay, let's just come back here. The thing is, we've just introduced the concept of probabilities and all that. Okay, so given a whatever experiment that we do, or statistical experiment that we do, whatever, okay, we can talk about the probabilities of certain events happening as we go. But the thing is, we are mathematicians. Would like to have our things done in numbers, okay, so that we can use the mathematical method with them. So rather than to have a coin which gives us head or tail, maybe we can assign them numbers like 0 and 1 instead, okay. And obviously if we have a die, a 6-face die, then it will be obviously 1, 2, 3, 4, 5, and 6. The thing is, we like to have our outcomes described by numbers. So we have what is called random variables. Random variables, okay? A variable, okay, that changes, okay, randomly. It may occur any one of them was something like your die or your coin. If we could have our events or what described by numbers, then we can talk about probabilities in terms of mathematical functions, okay. Again, if we have those, then we can do all the mathematical methods. In particular, we'll be using things like functions, and therefore things like differentiations and integrations and whatever we may have, okay. So we like to have these things given in probability distributions or probability distribution functions, okay. But then if you think about that, our random variables, it can be a number of things. You know, say for instance, if you have a coin, it'll be 0 and 1 representing head or tail. If you're having a certain game, having a gambling game, like if you throw a head, then you win $10. If you throw a tail, then you lose $5, etc. Then it will be the outcome would be like a plus 10 and minus 5. Okay, then you can have all the calculations involving all the functions. If you are throwing a die, it will be 1, 2, 3, 4, 5, 6. But again, there are other things in reality, such as if I were to have a test or have a check of people's height. Okay, so these numbers. It's not necessarily like a die where you have 1, 2, 3, 4, 5, 6 discrete numbers. For those, like a coin, like a die, it will be what we call discrete random variables, where the outcomes are given by particular numbers, 1, 2, and they have nothing in between. Okay, unlike continuous random variables, like if I'm measuring height or weight of people, if I am collecting a certain chemicals that are a gaseous chemicals that are after like experiment, okay, I can have all sorts of amounts given in this cubic centimeters, etc. Okay, these numbers can be anything really, so this can be continuous. We have to distinguish between the two because the calculations are slightly different for them, although the basic ideas are just the same. Here's the thing, suppose that we've got, dice, I like dice, so if I have a fair die, assume that we have a fair die, then the probability of getting a 1, which equals to 1, if I've got x, that's the number shown on a die. Okay, I assume here we are doing a 6-face die and not like 8-face or 20 faces. Okay, so that if suppose that we've got a fair die, so the probability of getting a 1 would be the same as probability of getting a 6. It'll be just 1/6 anyway. Equally likely to show. Yeah. On the other hand, if we are throwing two dice, if I'm throwing two dice and consider the sum of these numbers, then it could be 2, 3, 4, and of course you're not getting one. The total of a one there, the total could be 2. That means you're throwing a 1 and 1. But you can also get all the way up to a 12. So you are getting a 6 and a 6 on two dice. But this time you will notice getting a 2 will be just as likely as getting a 12 because you're getting two ones or two sixes. But getting things like a 7 would be more likely because you can have different combinations such as 1 and a 6, 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2, and a 6 and a 1 on your two dice. So they're actually 6 out of 36 possible combinations. 6 out of 36 possible combinations. While these guys, they have only one of the 36. Okay, out of all 36 possible outcomes, you got two dice to throw. Okay, all the combinations that you can have, there's only one of them to give you the 2, and one of them give you a 12, but 6 of them to give you a 7. I don't know how many of you are familiar with the that casino game, almost like called crab, that sort of thing. So you have to throw two dice and keep throwing a 7. Yeah, that's the sort of thing that suddenly comes to mind. Keep throwing a 7 with two dice here. How is it? Why 7? Okay, because that's the one that comes most likely if you have two dice. On the other hand, if you are throwing three dice, a typical casino game here, and if you throw this, so if the total of these numbers goes all the way from 3 to 18, and of course, you've got all sorts of combinations, and the distribution is given by this little graph here. Okay. Yes, you may notice it looks kind of like a curve going like one of those bell-shaped curves. If you're familiar with those statistical functions such as normal distribution and all that, and it's not exactly that yet, but it's still symmetrical, nice. And then what you're noticing here is we have discrete numbers. Our outcomes comes in 3, 4, 5, 6, 7, 8, 9, 10, etc. You never get anything like 6.352, okay, or anything in between. So they are discrete random variables. If you're throwing three dice, even if you're throwing three dice, discrete random variable. Okay, the total of the three dice. Okay, but it'll give you a nice little curvy picture here if you try to connect the dots together. So it doesn't make too much of a difference if you're considering the total probabilities and all that. Okay, what do we know? What do we need to know about probabilities is that, okay, for probability with random variables, the thing is, it'll be nice. Okay, again, it'll be nice if we can have a function. It'll be nice to have a function representing these probabilities so that if you have x equal to, I don't know, it has to follow some sort of rules here. Such as fx equals to x, it has to be bigger than or equal to 0. Okay, no matter what you put in, your probability must be bigger or equal to 0. And if you try to add them all up, all the possible probabilities, it must equal to 1. Okay, these are the two basic rules for probabilities. Everything is bigger than or equal to 0. Of course, if you want, of course, it goes also less than or equal to 1. Okay, but it's also included in the next line here. If you add up all the possible probabilities, you must get 1 exactly. So in order to have a function representing these probabilities, okay, you must follow these two rules. So given a function, you can actually check whether it is a nice or valid probability function or probability distribution function. This is the binomial distribution. Actually, I'll begin with the uniform distribution. I think you did. This one is easier. The uniform distribution. Uniform, as the name suggests, it goes all the way from x equals to 1 to to n. I'm doing this with discrete random variable. I'm doing the discrete version of the uniform distribution. Discrete version of the uniform distribution so that your axis goes all the way from 1 towards n. Like a coin, just 1 and 2. Like a die, that's 1 to 6. And all the probabilities equals to, or whatever, or what do we call this? We give it a name, we call it, actually, I'll just give you the function first. Okay, a uniform distribution. The nice thing about the uniform distribution is the probability is all the same for every value of x. Okay, for whatever x that you put in, okay, whatever value of x that you put in, you get the same probabilities for each of them, like your die here, 1/6 for each of them. We're going to call this, okay, f of x. Give it a name. I'm going to call this f of x. This is what we call a probability mass function. I'll explain this later, but it's a probability function. The function that tells you exactly the probabilities of these things. Okay. A simple, if you try to draw this on a picture, it'll be just a constant function all the way along. So 1, 2, 3, 4, n. 1, 2, 3, 4, n. Okay, all of them, just a constant function, easy. What we can do with a probability function is that, okay, I've got a function, I have this graph drawn so I can find out the probability for each of the values of x easily. What other features do we need for our probability function? Okay, another thing that we can consider is the cumulative probability. Okay, the function is what we call the cumulative distribution function. Okay, so if probability mass function for discrete random variable, the probability mass function is the function that gives you the exact probabilities where x equals to x. But sometimes, just sometimes, we prefer to have our probabilities given in terms of probability of x less than or equal to little x. And what I would like to have these probabilities like added together. All the probability added, like in this case that is f of x here, added together. Sometimes it's easier to sometimes it's just easier to work with, so that if you have something like f of 3, it will be just 3 over n in this case. just having everything like that. And this, and the reason we're having this is we want x to belong to the real numbers. Okay, the one before x takes specific values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., all the way to n. So that it's really just a little crosses on your graph instead of a nice straight line like this. But to have our so that this is not as easy for us to apply those mathematical methods. Remember, the whole point of having a random variable is that if these things can be represented by functions, then we can do mathematical methods on them. But having a function that gives us a lot of crosses, still good, no problem. But maybe sometimes, just sometimes, we may prefer to have a function written in terms of a continuous function. Well, no, not sorry, I'm not sorry, I don't mean continuous. A function defined on all values of x, defined on real numbers. So that in this case, my function for big F would go like it's been 0, or I'll change the color. I'll change the color. So it would have been 0 all the way from here. And when x equal to 1, it goes here. Okay, I've got 1, 2, 3, all the way to n. Okay, when x goes to 1, it starts to have some value like 1 over n. And when x equal to 2, it jumps up to another value like 2 over n. And it continues because we're talking about the probability of x less than or equal to x. When we put x equal to 2 there, it'll be x less than or equal to 2. That's x equal to 1 and x equal to 2 there. So you have 2 over n. But if you put x equal to 1.5, for instance, f of 1.5, it means what? Probability of x less than or equal to 1.5. What does that mean? X equal to 1 or only, because there's nothing in between 1 and 2. There's nothing in between 1 and 2. You can only take x equal to 1 or x equal to 2, x equal to 3. You can't, of course, put x equal to 2 in here. So this is all you're going to have, x equal to 1, and therefore it's just 1 over n. So this function is it goes up in steps. It starts with all the way with 0, and as soon as x gets to 1, then you get something like 1 over n. And it stays that it's 1 over n all the way to x equal to 2, where you go up to another level, 2 over n, and so on. And finally, when it gets to the top, and of course it will be 1. Okay, when it goes to n, then everything up after, for anything after when x is any bigger than n, you get f of n equals to 1. Okay, so then your function says x over n. Sorry, not x over n, I don't like it. Okay, this is what some people may prefer to see the distribution function, or sometimes they just call this the distribution function. But if you want to be clear about these things, you may just add it's cumulative. It's the cumulative distribution function. Again, if you try to use your Excel to work with probabilities, okay, you use Excel to work with probabilities, you will notice there's a cumulative button there. Let me show you. Excel, okay. You can do all sorts of popular probability distributions, like more, if you just go to formula, more functions, statistics, we've got binomial distribution, which we will talk about in a minute. Okay, and we have things like gamma, which we probably wouldn't touch that. Gamma. We have normal, the one that you have to know, normal distribution. Poisson. Poisson, another one that we will talk about in a minute. And well, and we've got other things like T distribution and all that, but let's not worry about that for now. Okay, which any of these things, let me just pick out the binomial distribution for them. Okay, you if you use Excel, then you know you put in your number in this case for X trials, what for whatever things that we shall see probability. And I want you to notice the last one is cumulative. They always give you this extra thing that cumulative, whether you want your probabilities like X exactly equal to X or you want X less than or equal to X. Nowadays with Excel, they will just do this all for you. Okay, but in the old days, we may prefer to, well, we may have to do these things separately. Having the probability mass function is one thing. Adding them together to have a cumulative distribution function is another. Okay, so given a random variable, given a function, you may consider one or the other of them. Okay, using the probability of these guys. Yeah. Okay. So let me just begin with the binomial distribution, the one so well popular. To use. We're going to introduce a few special or popular distribution. This, and we begin with the binomial. The binomial distribution is like this. Suppose that you have to repeat a certain experiment n times. Okay, like throwing a coin, like throwing your die. Okay, but not exactly right when you're throwing, not exactly applies to throwing a die. Suppose that you're repeating something n times, and we want that to be independent. Each of them, the results to be independent of each other. Like if you throw your coin, the results, each throw, the result of each throw has nothing to do with when another. Yeah, so they're independent trials. Repeat that n times, and where each time you've only got two possible outcomes. In a coin's case, it'll be head and a tail. In reality, we just call them success and failure. Okay, you may imagine you throw your coin, and then if you get a head, you call it a success. If you get a tail, you get a failure. Okay, anything that comes, well, repeated trials. That involves repeated trials, and each time having two possible outcomes. Okay, with probabilities p and 1 minus p, or sometimes we just call it q. We're just too lazy to keep writing 1 minus p, so we just call it q. So, or one or the other. So if you just keep 1 minus p, or is just as fine. Okay, like throwing your coin, like repeating anything, really an experiment. Okay, like playing a particular game where you have a fixed probabilities of winning. Okay, you either win or you either or lose. You're either success or you're a failure. Okay, taking a test, and or even honest, just a joke, asking a girl out, asking your girl out. So you may succeed or you may fail. Okay, and just imagine you ask the same person a number of times. Okay, n times, and see what happens. Where at the end we can then represent the probabilities of getting x successes. Okay, you're repeating this n times, and you're thinking the x successes. Imagine again your coin, throw this like 10 times. What is the probability that you will get 3 heads? Okay, I always take the coin as an example because it's easy to understand. If you throw your coin 10 times, what is the probabilities that you would get 3 hits? Then what would happen is, because these things are all independent, okay, so that when you have to get 3 hits, no problem. And you're trying to throw a coin here, a fair coin, fair coin, so that P equals to a half, getting a hit. So you get 3 hits. Don't forget, many people would. Okay, if I ask you what is the probability of getting 3 hits when you throw a coin 10 times, that means not only you're getting 3 hits, you're getting 7 tails. You must not forget that this extra bit here. So we have these guys half 0.5, if you like, to the power 3 times 1.5 to the power 7. Fine. But there are a number of ways you can achieve 3 hits in 10 throws. Maybe you get your 3 hits in the first 3 throws and then get tails after that. Or you may get your 3 hits like in the 6th, 9th, and the 10th throw. Then you still get your 3 hits and then you get tails otherwise. There are a number of ways you can achieve 3 hits. So we have to multiply to this binomial coefficient I showed you the other day, which if you prefer, you can write it like this. NCR notation, NCX combination notation. The number, that is, if you remember, the number of ways to choose X thing from N, the number of ways you can have X hits from N throws. Okay, so we have this thing here. It's not a factor. It is the binomial coefficient here, nx, like this. Okay, so this is the probabilities of having x successes if you're repeating a certain whatever experiment n times, each with a success rate of p. And this x, of course, can go all the way from 0 to n. You may get no hit at all, or you may get n hits. Okay. Okay. Okay, this is a binomial distribution. Sometimes it's it's B for binomial. Sometimes people give it this name, the name B, N, P. There are two things that this distribution has two important numbers. One is the N. How many times are you repeating this experiment? How many times are you throwing this coin? The other one is your P. What's the probability of having a success? Okay, these are the two numbers. So we often say X has a distribution of binomial with N and P like this. And this function here, probability of X equals X, okay, the probability mass function that I had, in this case, we call, in my PowerPoint, I'm calling this P, but sometimes, again, some textbooks, they prefer to write specifically, okay, B for binomials. So it's a function a function of X, but it contains the parameters N and P. N and P. Whatever you have here, it's the same thing, N, X, P to the power of X, and Q, 1 minus P to the power of N minus X. You succeed X time, but that means you will fail N minus X times. The reason it is called binomial distribution, I don't know if you wonder why it has this name, binomial distribution, is if you try to consider the sum of these probabilities P and Q, maybe Q equals 1 minus P, okay? have this to the power of n. On one hand, you know that p plus q is simply 1. 1 to any power is just 1. But on the other hand, if you expand this bracket, if you remember how to expand this bracket I showed you the other day, can you expand this bracket? P plus q to the power of n. What do you get? You get p to the power of n plus n times p to the power of n minus 1 q plus n2 times p to the power of n minus 2 q squared plus dot 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 all the way until n minus 1 p n minus p1 q n minus 1 plus finally q to the power of n. Again, if you're familiar with these binomial coefficients, that's what we call the binomial theorem. Okay, this is what we call the binomial theorem. Bi means two. That means two things here. The binomial here is what we have two things added. So we have the bi here, and then we have got this power bracket to the power n. We know this expansion before. Again, if you don't remember how to expand these guys, you have your Pascal's triangle. Etc. Yeah, your Pascal's triangle. Allowing you to expand these brackets. But the binomial theorem tells us this thing here, and each of these terms you probably would notice is just p of x being n plus probability of x n minus 1 plus we're having n successes, n minus 1 of them, and all the way to 1 success and all failure. We've got this thing here, just to confirm to you that when I add up all the probabilities together, I do get one. Okay, remember, given a function, okay, it is important to check whether it is a valid probability distribution function, a probability mass function in this case. Each of them being a bigger than or equal to 0 number. The other thing is, if you add up all the probabilities together, you get 1. This is it. So this is nice probability function. Okay, and the picture is actually pretty much like the one we had earlier, the curve, the bell-shaped curve here. But depending on the size of p, you may get something heavier on one side or the other. Okay. So if you imagine you have a p exactly equal to 0.5, then you will have something perfectly symmetrical in the middle. But if your success rate is smaller than your failure rate, that means you're more likely to have failures than successes. That means that at the end of the day, after n trials, you will have you will have more probabilities of having fewer successes, x being smaller. Okay, so it will be skewed this way positively. We call this positively skewed graph. This is heavy on one side, and of course, if you have p a lot larger than q, then the picture can go all the way like that way, skew negatively. Negatively skewed, and we have positively skewed. Okay, if p equals 0.5, then you get something completely symmetrical in the middle. So we understand these functions. So we can just each time we just put a number in. In this case, if you are to answer my question earlier, you have the 10, 10 throws, 3 heads. 10 throws, 3 heads. You know that P exactly equal to 1/2 if you're talking about fair coin, N equals to 10, then the probability of X exactly equal to 3 heads would be like what? 10, 3, I'll use a half. I'll use half. Okay, 3 times half, and then 7. And of course, you need a calculator for these things. Okay, or Excel, as I can show you here, binomial distribution. Number 3, I'm getting 3 heads from 10 throws with a probability of 0.5 each time, and I want this to be false. I would like to find the probability of X exactly equal to 3 only. Then I can work out the probability here. In this case, if you can, okay, 12%, 11.7 if you like. There to be 11.7%. Okay. On the other hand, if I prefer to work out P less than or equal to 3, really, you can do this by working X equal to 0 plus X, P of X equal to 1 plus P of X equal to 2 plus P of X equal to 3. You can do it, you can find the probability of X less than or equal to 3 by working out all 4 of those probabilities and add together. But this, again, this Excel and all the thing here allows you to do 10 throws, 0.5, and then by putting a true there, it gives you this number automatically. So you don't have to do all 4 of them added together yourself. 17%, 17.2. Okay. Okay. And sometimes, okay, if you don't have Excel, I don't know if you have seen this before. In the old days, people have, before the times of computers, Excel and calculators and all that, people had tables. People had these tables involving probabilities and statistical functions. You can check. You can go to the internet and have a look for binomial distribution table. You will see something like this. Okay, it gives you the probabilities of, you see, you've got the picture here, having all these values of these probabilities going up like this, and then down again. And they give you the cumulative probability, binomial probability of X less than or equal to X in a table like this. So all you need to do is look up the value N, like N equals 5, N equals 7, N equals 10, etc. I'm doing this for 10 throws, so our N equals to 10. And I'm looking for probability of 0.5 in this case. Okay, 0.5 for P. Then we can look up X less than or equal to 0, X less than or equal to 1, 2, and 3, etc. You can see that I've got 0.1719 for X less than or equal to 3, the one that we actually got. Okay. In the old days, that's how people look up probabilities like this. These tables, they don't give you X exactly equal to 3, X exactly equal to 2, X exactly equal to 5, that sort of things. They give you these numbers because if you really want x exactly equal to 3, all you need to do is probability of x less than or equal to 3 minus probability of x less than or equal to 2. In this case, we can look them up from here. 0.1719, 0.0547, 0.1719 minus 0.0547. And we just need to do a little subtraction to see we've got something like 11. I've got a 9, I've got a 7, I've got a 2 there, and I've got a 144, it's a 7, like this. Same as what we got earlier. Okay, that's how we use these tables in your exam. Okay, I mean, if you were doing this course with me face to face, then in our exam, obviously I can't allow you to bring in a computer, so I'll be giving you these tables, so you need to be able to read them and look up numbers from them. But now, since we are doing this online, I don't know. I will still provide these tables just in case, but I I don't see I don't see how I can stop you using Excel to do these calculations. So I have to think about your exam question, how I may set your questions so that you can so that you wouldn't obtain your answers too easily. Okay. But of course, I mean, with Excel, you get everything immediately, just a click. Okay. So yeah, in the old days, I'm showing you here. In the old days, that's what you would have. I've got this table to look up values of these things. Okay. All right. We can work out these things, but what other features what other feature is a probability distribution? I mean, what is important in a probability distribution? We have the mean value. We have the mean value and the variance value. Okay, the mean value is like the average. We talked about this there. The mean value as the average of your distribution, or the average of the data, or whatever. For probability distribution, mean value is sometimes called the expected value. Okay, like the average, you see, the expected value. So if you are throwing your coin, if you're throwing like your coin 100 times, you expect to see 50 heads and 50 tails. Okay, so you would that sort of expectation. If you are again having a gamble where you may win money, you may lose money. Okay, success, then you win. Then there's failure, you lose money, and then you work out the expected value. If it is positive, that means you're expecting to earn money out of this gambling. Okay, then you would go ahead, obviously. Then if you are getting a negative expectation, it means that you are likely to lose money in the long run. Okay, I don't know if you have been to casinos and have to be a casino before. Uh, we, a lot of these, or if you've seen these things in movies, in the casino games, most of them are very easy, straightforward for you to play. Okay, you just bet on whatever things you can see, and then you either win or then you lose. But all the calculations, there are complicated calculations before they invent one of these games, and every time, okay, no exception. All of these games, they are designed to have a expected value of negative numbers. So if you walk into a casino, okay, if you keep playing a game for long enough time, you'll be expected to lose money. Okay, casinos, they don't have to cheat on you. They don't have to do silly tricks. It's the games that they set up, they're designed like this. It looks as if that you just have half of 50% chance of winning or something like that. But you can imagine if 100 people walk into a casino, then 50 people win, 50 people lose, then at the end there's nothing for the casino to earn. Okay, so these games, they always comes in a little negative expectation, so that if you get some people walk into a casino again, eventually, okay, people come and go, but eventually, like 51% of people lose, and then 49% of people win. Then there's a little margin of 2% or one point something percent. That's what the casinos are making. Where the casinos are making money. Okay, of course, we're not doing gambling theory in this course, so let's just stop here. But here's the thing: the expected value is given a probability distribution x equals x. I know that if I add them all up, it will equal to 1. If I add up all the probabilities together, it will equal to 1. But for the expected value, I multiply them by x before I add them up. Okay? So if you're throwing a coin, okay? So if you're throwing a coin, that means for a coin, that means you're having 0 if you're thinking for coin, 0 for a tail, and 1 for a head. Then what you do here is you get 0 times a half plus 1 times a half expected value of x equals to 0.5. Okay, this is what we call expected value. This 0.5 here means that it doesn't mean if you throw a coin you are going to get 0.5 of a head. No, it doesn't mean that. It means if you are throwing your coin 100 times, half of them will be heads, or 50 of them will be heads. Okay? Expected value, it doesn't necessarily mean that it will happen in reality, but it's a number that you would expect to see on average. Okay? So you have this guy. On the other hand, for the variance, if you like to talk about the spread of your distribution, as you saw the picture earlier with the binomial distribution, it's a spread out distribution. What you do is you consider your x's. Okay, again, you've got your probabilities of x equal to x. But the thing is, we want to check out the spread out of your distribution. So we're not working with x. We're working with x minus. Sorry, mu. Another name that we give for mean. If you say e of x, if you have e of x here, it means expected value of x. Mu is just a Greek letter for m. M for mean. I'm just being lazy. I don't want to write e of x here, so I'll just use mu. We consider the difference of x from the mean value, from the middle of the distribution. We consider how far away each of these x is from there. But again, when you do that, sometimes you'll get positive value, sometimes you'll get negative value. When you add them all up, that's no good. They will just cancel each other. So for variance, just like what we did with explained before, we square these guys before we add them. Okay, with these guys, x minus mu, we square them and multiply to the corresponding probabilities before we add them all up. That's what we get for the variance, and sometimes sigma square. Okay, or again, depending on what sort of textbook that you use, you may see variance of x or sigma square. Okay, and if you want standard deviation, okay, We just take square root. That's sigma. Okay? You just take this guy and take square root. Okay? So you can work out the given the probability distribution, maybe binomial, maybe other distribution, you can work out the mean, the expected value, or the variance. Okay, how far it is spreading out. So you can imagine, because the normal distribution is one of those bell-shaped curves, yeah, as you saw with this picture, the numbers are more closer to the middle numbers, and you are getting less probabilities on the either end, where x equal to 0 or 1 and x equal to n or n minus 1. That's all. You can so you can see that variance is going to be slightly smaller compared to things like the uniform distribution. Yeah, you can do this calculation for uniform distribution, because for uniform distribution, okay, the probabilities is the same for every single one of them. If you think about the picture, it's actually very spread out. Every number is just as equally like as each other. So you will get you will be getting a larger variance or standard deviation value for a uniform distribution than a binomial distribution. And for a uniform distribution, the middle is just somewhere in the middle. Okay, if a coin there, it will be 0.5. If you got a die, 6-face die there, it will be 3.5. Again, it doesn't mean that you're throwing 3.5 from a die. It means that on average, if you throw this 100 times or 1,000 times, the average of each throw will be 3.5. Okay, so for a binomial distribution, you can actually show that the mean value of this and the variance of this distribution, it involves a little mathematical tricks. Okay, it involves a little mathematical tricks. If you try to multiply this function p, if you try to multiply this function by x and then add up, okay, it takes a little mathematical skills to turn this into simplified to a mean value n times p. It can be found in any probability or statistics textbooks, really. Okay, similarly for the variance, as it turns out, the variance is simply n times p times q, or 1 minus p if you like. This is the variance. Okay, mathematically we talked about that. Mathematically, we'd like to use variance rather than standard deviations, because we simply don't like the square roots. Okay, but nothing wrong with the standard deviation here. Okay, let me give you an example, a quick example here. Suppose that we've got a restaurant. Okay, suppose that we've got a restaurant, and of course we've got customers coming in and out, and we notice some of our customers are smokers. We notice that some of our customers are smokers. So I'm thinking, we're thinking to have smoking areas in my restaurant. So I have a little areas, okay, only for smokers, and then we have non-smoking areas for the rest. Okay, but obviously I don't want this restaurant to be completely non-smoking one, so that I would upset the smokers, because the smoking customers, or vice versa. I don't want to make it a completely smoking restaurants, so that I will lose the other half of these customers. So what do I do here? I'll just have a little quick survey, or a little quick experiment, checking out what proportion of my customers are smokers. In this case, 42%. 42% of these customers are smokers. So I probably, if I have a capacity of 80, if my restaurant can fit 80 people, how many seats should be available for smoking area? So given that I've got 42% here, I I've got 42% here for a customer to be a smoker. So I've got 80 seats. So you can see that if n equals 80, then the mean value average n times p equals to 80 times 42%. I have something like well, 33 of them. If I have a full house, if I have a full house on a particular night, okay, 80 people, I will expect 33 of those seats will be filled by smokers, and therefore I should have my smoking areas by like 33 seats. But of course, on any night of we're not going to have only 80 people. Okay, in an evening, people come and go on a single night. We've got turnover, so we may have, in this case, 213 on a particular night. 213 on a particular night. What's the probability that there were 80 or fewer smokers? Suppose that we've got fat fingers. Suppose that we've got n equals to 213. Again, p being 42%. I've got 213 customers on a particular night. What is the probability that it is 80 or fewer? Okay. We've got n, we've got p. We have our formula here. As a customer is either a smoker or a non-smoker. So that it really is the probability of x equal to 0 plus probability of x equal to 1 plus plus probability of x equal to 80. Each one of them can be done by this formula here. But if I ask a question like this in an exam, you would curse me, probably. Less than or equal to 80. I've got 81 terms to add together. It will take me forever. Of course, I wouldn't ask you anything like this in an exam, but just as an example, we can do this with an Excel. Exactly the same way as before. I want 80, and I have 213 customers, where we have 42% of being a smoker, and I want probability less than or equal to this thing, 80. So I can have my probability given by 10.6%. Okay, it's like 10.6% here. Just by looking up from these tables, well, no, sorry, these tables, they don't give n as large as 200, okay? But Excel can certainly help you work out these numbers easily, yeah? In reality, in the exam, of course, I'll have to give you something easier to work with, okay? Smaller numbers so that you can work out these probabilities and add together, or just go to one of these tables and look up your probabilities, yeah? Simple as that, okay? Just very simple probabilities calculations, okay? I suppose I'll go to Poisson distribution like next time, okay?